Okay, in class we looked at piecewise functions, and piecewise functions are just a combination of equations, and each equation corresponds to a different part of the domain. So we're used to graphing equations, and we're used to seeing y equals. Instead of y equals, we'll just be using f of x, which is another way to express the range. We're going to graph our functions just like we always do. This is in the form y equals mx plus b. But what's new are these domain restrictions. We won't get to graph all of both equations. We'll just be graphing pieces, which is why we call them piecewise functions. What I want you to notice about these functions is one of the endpoints is open and one of them is closed. If there is a bar beneath your inequality symbol, you'll close the symbol, and if there is no bar underneath the inequality symbol, you'll leave it open. So what it looks like are just two different lines pieced together, and that's exactly what it is. A special type of step function, or special type of piecewise function, is a step function. It looks like little segments all together. It's notated with this double bracket, and when you see that double bracket, it means we are identifying the integers, the greatest integer that is less than or equal to a given value. So, for instance, this little symbol right here, you're not going to be able to find it on your calculator, but where you can find it is in some of the menus. If you have a TI, then beneath your colored buttons, there's a button that says Math. After you choose that Math option, there will be some menus, and underneath the number menu, you would choose integer at that point. On a Casio, you would use your option button, and underneath option, you would choose the number menu, and there's where you would find integer. You can plug those in and look at a graph of a greatest integer function. Okay. So if you have a couple of functions pieced together to form a piecewise defined function, then your x value dictates which of those functions you use. So if we're using an x value of 10, 10 is a number that is greater than 4. So that means I would have to use my bottom function, because my bottom function is defined for all values that are greater than 4, and 10 is bigger than 4. So that's why I chose 2x plus 7, but I didn't put in the x. Instead of the x, I substituted x with 10. So 2 times 10 is 20, 20 plus 7 is 27. If I combine the input and the output together, this is a point that is on the bottom piece of my piecewise function. It's one of the points that defines that function. So if x is negative 1/3, negative 1/3 is smaller than 4. So only my top function is defined for domain values smaller than 4. So this time I have to use the top function. So I'll use 3x minus 1. But instead of x, I'll substitute in negative 1/3. The 3's in the numerator and denominator will cancel, and I'll end up with a negative 2. So I put in a negative 1/3. I got out a negative 2. That is a point on the top piece of my piecewise function. So if x is exactly 4, then that's when I have to start looking for the bar underneath my inequality. So since my top function has a bar underneath the inequality, I'll use my top function. It's defined when x is exactly 4. So I'll use 3x minus 1, but instead of x, I'll replace it with a 4. And 3 times 4 is 12, minus 1 is 11. So if I combine my input and my output, this piece is a point on my top function. And then again, if you've got a value less than 4, you'll use your top function. Instead of 3x minus 1, you'll replace the x with the given value, and you found another point on the top piece of your piecewise defined function. To graph them, we graph just like we always did. So instead of this f of x applies to both of these functions. And we know that f of x and y are equivalent. So I just separated them, and I wrote them in y equals mx plus b form. So remember, you always start with your y-intercept. So the very first thing you should do is put a point on the y-axis at 1, and from there you should rise to run 1, Or the alternative is to move down 2, left 1, down 2, left 1, down 2, left 1, and that will graph your line, but you don't get the entire line. You only get the line over a restricted portion of the domain. So you only get to draw that line to the left, or when x is less than 1. So that's why I didn't continue this line. I only drew the line to the left of 1 on the x-axis. So your eyes have to drop down and look at the x-axis to know when to stop. Same thing with our second function. I just rewrote it and made all the pieces show. There's ones that you can't see, but we always start on the y-axis. So we would start at 1, 2, 3, 4, and then we would move down 1, right 1, down 1, right 1, down 1, right 1. And I could continue this line backwards, but I won't because the domain is restricted. I only can draw this downhill line to the right of 1. Now what I want you to notice is one of these inequalities has a bar and one of them doesn't. They overlap, so often I'll draw an open circle and then I have to turn around and fill it in for my second piece. This function would go forever to the left and it would go forever to the right, so there is no restriction on the domain. The domain is all real numbers. However, this function, this piecewise defined function, never rises higher than 3 on the y-axis. So all of my y values are lower or less than 3, but we used a solid dot here, so we are including 3, so I'll put a bar underneath my inequality. All right. For this little step y, or for the little step function, remember this f of x applies to everybody inside of the brace. So this f of x belongs with each of these pieces. However, you may be more accustomed to seeing it as y equals 4, y equals 5, y equals 6. That is a horizontal line. It's really a line that would go all the way across the page where y is 4. However, we only get to keep a part of that. So here's the restriction on the domain. I only get to draw this horizontal line at y equals 4 when it's between 0 and 2 on the x-axis. So my eyes are traveling down to the x-axis. And that defines the width of that piece of the piecewise function. So when I move on to the next piece, I should draw a horizontal line all the way across 5, except that my domain is restricted. So I only get to draw a horizontal line at y equals 5 between 2 and 4 on my x-axis. So it forms little fences is what happens. Same story. So I feel like I want to draw a horizontal line all the way across y equals 6, but I can only have a piece of it because this is a piecewise defined function, and that function is only defined between 4 and 6 on the horizontal or the x-axis. Okay. You can also work backwards and write a function. So this point does not contact the y-axis, but if it did, if this line did contact the y-axis, it would happen at -1. And the slope appears to be rise 1, run 1. There's not a 1 here, but you can imagine it being there. However, that line only exists to the left of where x is 0. It stops right below where x is 0. And this endpoint is open, so that's why there's no bar. So now I'm going to move on to the second piece of the line. It definitely does contact the y-axis at 2, so that's why my y-intercept is 2. And the slope moves down 1, right 1, down 1, right 1, down 1, right 1. So you can imagine these ones here. However, that piece of the piecewise defined function only exists to the right, not of 2, but to the right of where x is 0. It begins right above 0 on the x-axis. This dot is solid, so that's why there's a bar. Okay. Then for the step function, it's made out of 3 little horizontal segments. The first segment, I would look on my y-axis to establish the name of the horizontal line, but when I'm looking at the restriction on the domain, my eyes would look to the x-axis. So it is true that this is a portion of the line y equals 1, but it only exists between 0 and 2 on the x-axis. Okay. If we allowed this second segment to move in both directions, it would have contacted the y-axis at y equals 3. That's the name of this line, but we only get a piece of that line. And we only get to draw that line between x equals 2 and x equals 4. So when I'm thinking about the domain, I look at the x-axis, not the y-axis. So that piece only exists between 2 and 4. One of the dots is solid, one is open. One is solid, one is open. That's why one of the inequalities has a bar and one does not. This would be the line y equals 5 if we got to draw the entire line, but instead we just have a piece of that function. And the piece we have is between 4 and 6 on the x-axis. So this function is only defined between 4 and 6 on the x-axis. The last little exercise we did was about parking rates at a garage, and it says that it costs $3 per half hour. So if you haven't parked in this garage, you don't have to pay anything. So that's why this point is open. All the way up to 30 minutes, which is half of 1 hour, you'll pay $3. And even at 30 minutes, you'll still only pay $3, which is why this circle is open. But on the 31st minute, all the way to the 60th minute, now you'll pay $6 for parking in this garage. At 60 minutes, you'll still only owe $6, but on the 61st minute, you'll be charged $9 thereafter. That continues, it says, all the way up into a maximum of $18. So when we get to $18, that's the maximum amount you'll have to pay for 12 hours. And remember, this little notation means that something is missing from your graph. Not all of this is showing. So 4 hours, 5 hours, 6 hours, 7 hours, not all of that is showing. Some of it is hidden. And remember, that's what that little notation means. Okay, now you're ready to do your homework problems and come in and take your quiz. Good luck.